And finally, as a practice, let's try to prove the NP-completeness of another problem in formal language. Okay, suppose that we already know that the click problem is NP-complete. Let's try to prove that the vertex cover problem is NP-complete as well. So the click problem is this. Given an undirected graph G and an integer k, does this graph contain a complete subgraph, a so-called click, of at least k vertices? Well, actually, the original problem is to find the maximum click in a given graph. And this is the decision version. So for any integer k, does this graph contains a click of size k? Okay, and that's the click problem. And the language click is the collection of instances G and K such that G is a graph which does have a click of size K. So those instances that will answer yes to this question. Okay, and that is the language click. And the vertex cover problem is, given an undirected graph G and an integer k, does this graph contain a subset of vertices so that the size of the set is at most k, and every edge in G has a vertex in this V prime, and so-called vertex cover. Cover means to cover all the edges. Okay, so the original problem of vertex cover is to find the minimum vertex cover, and that is to find the minimum subset of the vertices so that every edge in G has at least one vertex in this set. And the vertex cover language is the set of instances of graphs and Ks so that this graph has a vertex cover of size k. Alright, now we're supposed to prove that this problem is NP-complete. So the first thing to do is to prove that this problem is in NP, right? How are we supposed to prove that? Do you still remember the definition of NP in formal language? It means that we need to find a verification algorithm, and that for each instance G and K, we can find a certificate Y so that this verification algorithm can verify the answer. Right? So given any instance X, which is a specific graph and a specific K, we take any subset of the vertices as the certificate Y. And the verification algorithm is to check two things. First, to check if the size of this subset is exactly k. And the second thing is to check if for every edge U and V that at least one of them must be in this subset. Okay, and so what is the time complexity of this verification? Since we have to check for every edge, and in the worst case, the number of edges would be v squared, or say n squared, right? For every edge, we need to check its two endpoints, right? And to check if at least one of them is in this vertex set. So in the worst case, the size of this vertex set is just n. So altogether, it's going to be big O of n cubed. So that means we do have an algorithm that can verify this language in big O of n cubed time, and therefore it is in NP. Okay, now next we're supposed to prove that the click language is no harder than the vertex cover language. So how are we supposed to prove that? We're supposed to start from any instance in the click language. Okay, so suppose this is the original graph we have for the click language. And this is the complement graph. Complement graph means the graph contains all the vertices and those edges that are not in the original graph. Then we want to prove that G has a clique of sides K if and only if the complement of G has a vertex cover of sides V minus K. So in this example, it means that if the original graph G has a clique of sides 3, those red vertices belongs to the clique of sides 3, right? And it's equivalent to say that the complement of graph has a vertex cover which contains the blue vertex of sides V minus K, which is 1. Now let's try to prove it. We start from assuming that this G has a clique V prime of sides K. Now let's consider the blue edges that is in the complement of G. Okay, let U and V be any edge in the complement of graph. Then we see that at least one of them does not belong to V prime, does not belong to the red set. How come? We can prove by contradiction, right? If this is not true, then we say that there's one blue edge such that both of them belong to the red set. Both of them are red. And what's going to be wrong? And because this is a complete graph, right? So-called clique. Clique is a complete graph. And therefore, if two vertices are in this clique, then the edge between them must belong to G, must be red as well. And it cannot be blue. So that is the contradiction. So we have proved that for any blue edge, at least one of them must be blue. So it means that at least one of them does belong to V minus V prime, which is the blue set. And since this edge is any edge in the complement graph, it proves that every edge of the complement graph is covered by a vertex in the blue set in V minus V prime, and the size of this set is V minus K. So therefore, the set V minus V prime, which has the size V minus K, forms a vertex cover for the complement of G. Okay, that's the proof of one side. And the other side is that we assume that the complement of G has a vertex cover V prime of size V minus K. And that means since this is a vertex cover, it means that for all the pairs of vertices U and V, if this edge is not in E, which means if this edge is blue, then one of them or both of them must belong to this V prime, since this is a vertex cover and covers every edge that is not in E, that is blue, right? And in other words, it's equivalent to say that for all the pairs of U and V, if U is not in V prime and V is not in V prime, then this edge must be red, right? We'll say if this edge is blue, then one of the vertices must be in V prime. If none of them are in this V prime, then this edge must be red. Okay, get it? And if a vertex is not in V prime, then its color must be red, right? Which means for all those red vertices, there must be an edge which is colored red. Okay, which means that all those red vertices forms a clique. It's a complete subgraph, and it has the size of V minus V prime, which is K. Alright, so we have proved that we can reduce clique to vertex cover. And the last question is, can we do this in polynomial time? That is to ask whether or not we can obtain the complement of a graph in polynomial time? And the answer is certainly yes. It's trivial, right? We only have to check every edge and to make this complement of graph, right? And that completes the proof.